Today I want to cover a solar panel array. The last video was on a single solar panel. Now we're going to discuss joining this together to form an array. First thing I want to do is invest the series connections to increase the voltage. The current would remain the same. Then we look at some real test results and compare them to what we would have gotten in theory. Look at the theoretical IV curve and then estimate an IV curve based upon the limited test results we have. Do some rough estimations where the maximum power point would be under those test conditions that we had, and estimate the maximum power we could have extracted from this system. And then some quick discussions on blocking diodes, bypass diodes, and determine their relevance. I will get into the actual charging of the battery in another video because this will get quite long and possibly a bit boring. Looking quickly now at the configuration of the panels, 3 panels. On average we got 5.6 volts thereabouts for the first panel we tested. So assuming all the panels are identical from the same supplier, so they hopefully are. If we add up the voltages, because it's a series assembly there, we would end up at 16.8 volts. So we're expecting about 16.8 volts from this configuration. So let's go now to the actual installation and the recordings at that point in time. Pretty true. Put the main line here. This is speaker wire. This is not UV rated. Anyway, I'm going to put one more clamp here and one here so that we can pull out easily. And electrical tape on the back of this. Again, yeah, that's really going to hold for a very long time. So yeah, more of a test thing because I'm probably going to end up mounting these with mounting tape, which again, yeah, that's going to hold for a really long time outside in the weather. Finished arrangement with our mounting tape, scotch permanent mounting. Who knows how it's gonna hold? Supposedly 2 pounds. So negative, positive to negative, positive to negative, positive. So yeah. Alright, so all connections in. This has been wiped, so it's a little dusty still, but hope for the best. I'm gonna pull out this tape and line these up, press them in. Plastic off. This is our finished look. Initial testing position, this seems pretty good. On a lip, on a shed, sunlight is coming this way, down, afternoon sun. It's now starting to get dark, right? Great, so let's see what we get. With no load, 16.32. Let's jump a little bit into the theory of how a solar cell functions. What you see there, the red curve, that is the IV curve, current versus voltage. ISC is a short circuit current. That is when you have zero load on that solar cell and you basically short it off through a meter. That's what you're going to get measure. ISC, short circuit. On the other extreme of this, where the curve hits the horizontal axis, was the VOC, which is the open circuit voltage. In this case, you are drawing zero current because you do not have any load on it, and you measure the open circuit voltage. And in between, that's how it functions, the curve. If you notice, you can keep taking more and more, raising the voltage, and the current stays fairly high for a long time, and then it drops off very sharply. The blue line shows the power curve, and that makes sense. At the beginning, while the current is very high, short circuit current, the voltage is 0, so you'll get 0 power because power is VI. As you increase the voltage, it will the power will linearly increase, and that makes sense because if you're looking, the current isn't actually dropping or varying very much. So as you increase the voltage, there's a linear relationship. That all changes when the curve starts to tip downward, the IV curve. Basically, current is dropping, voltage is increasing, but current is dropping faster than voltage is increasing. So essentially, power starts to drop off faster. Power was increasing before, it reaches a point where power tables off to the top, which is the maximum power point, and then it starts to drop because the current is dropping way faster than the voltage is increasing. So power is of course going down. And again, it makes sense for the power to then again be 0 when you reach VOC, because power being VI again, if I ends up being 0, power will be 0. So the blue curve, if you look at it, that makes sense. And what we're trying to reach to is that maximum power point, the point when just a little less current is being pulled and just the right amount of voltage is being pulled to get the maximum power extracted from the solar cell. Taking this curve now, our theory, and let's bring in our practical example, what we've measured. From the last video, when I shorted off the cell, from the video pulling off what I've seen on the meter, it's 0.526 amps. That's what we're getting. And the open circuit voltage that we just measured a clip or two back was 16.32 volts. So now we have to kind of estimate how this IV curve works. We only really have two measurements, which is not really much, unless we go and load the cell along the way and take measurements all along the way. There's no easy way to get this curve. But the theory of it is the maximum power point tends to be about 92% of the current, and it tends to be between 70 to 80% of the open circuit voltage. So work with those rather generic assumptions. Let's work that with. Going with 75%, I'm getting 12.24 volts, and then going with 92%, 0.484 amps. Multiplying that out, 5.92 watts. Seems realistic, considering I was getting about 1.5 watts the last time. Seems a bit more, and the cells are already rated for 2.5 watts, so 3 of them theoretically 7.5 watts, getting almost 6 watts. Well, I guess that's not really that bad. I mean, as I said, Chinese can't expect to really get the exact rating. In fact, this day and age, nobody gives a real rating on anything. So that's why testing is important. Moving on to blocking and bypass diodes. Let's start with the blocking diode. Why do we need a blocking diode? Well, the equivalent circuit for a solar cell is actually a voltage source with a diode. So essentially, when we connect this in the night and the battery has a higher voltage now than the solar cells, simply because no light, so solar cells aren't generating anything of significance, and the battery is, let's say, 12.5, 13 volts, what have you. What's going to end up happening is the power from the battery is going to drain through the solar cells. It's going to heat up, it's possibly going to destroy them, and it is going to obviously waste all the power that we had from the day and everything else that was stored in the battery. So a blocking diode is absolutely essential. This clip here, I've put in a blocking diode that is a 1 amp diode rated, right? A simple generic diode. It's rated at 1 amp. In our system, we've never actually crossed 0.5 to 6 amps. So yeah, we're perfectly fine with that 1 amp blocking diode, and that will sort that part of the situation out. When the array was constructed, I did not in fact put in any bypass diodes, and that was based on the assumption that these 3 panels are very small, so the probability that one alone is being shaded is low, and it was meant to serve a power supply to a car battery, that being about 13 volts. It requires all 3 cells to really be active for you to get that voltage. 2 of them alone wouldn't get you. It probably gets about 11 point something volts, probably let's say 11 volts. So we still need the third cell to really cross over. Now, so that was the assumption, that was the theory there. That said, a partial blocking of the third cell or some kind of shading will probably get me over the 13 volts, which means that then the entire circuit is conductive, because the diode that was blocking the voltage as opposing, which is the battery, is now higher, and the 2 cells that are producing the full power, they are capable of generating the 0.5 amps. The third cell is not. Third cell will then have to dissipate the makeup amperage in between. So let's say the third cell is generating 0.1 amp, it'll have to dissipate 0.4 amps. It isn't that much. It's a big enough cell. It's not like a very large array. I don't think it will cause any problems. The bypass diode, really, as soon as you start putting load on those 2 cells, that power is going to drop down very low anyway. It's a gray area. To be safe, I should have put in one. I did not. I have not seen negative effects. But then again, the testing has not been extensive, and we'll probably touch a bit more on that when we start with the battery charging, and then try blocking our cell and see what happens a little bit more and see whether the array in fact needs to be modified.